So picking up where we left off, we had been looking at Lewis structures. Lewis structures is something that you should have learned about in Chem 3A. Formal charges are probably going to be new to most of you. Formal charges are something we cover in Chem 1A, but we usually don't go over in Chem 3A. And there's different ways of looking at the formal charge. This is a more mathematical way. We're looking at a Lewis structure with all of the lone pair electrons and all the electrons showing. So we're going to look at a Lewis structure, and then the formal charge is calculated for each individual atom. And to calculate it, the formal charge is equal to the number of valence electrons that that element has minus the number of bond, oh, that's even strange here, the number of bonds plus the number of unshared electrons. That's not actually quite correct. That's fabulous. It's the valence electrons minus 1/2 the bonds plus the unshared electrons, that quantity. So if you like mathematical equations, there it is. And we'll do at least one example here. In a neutral molecule, the sum of the formal charges is always going to be 0. In an ion, the sum of the formal charges for all of the atoms in that ion will equal the charge on the ion. And if our Lewis structure follows the idea of valence that we talked about, where carbon tends to form 4 bonds, and hydrogen forms 1, and nitrogen forms 3. If it's obeying those rules of valence, then generally the atoms will have 0 formal charges. A 0 formal charge is generally more stable. So let's just look at, I'll just make up some examples, or maybe I'll borrow some from the book, because I don't, oh wait, is there some here? Oh, that's not a good example. Okay, this is where I did not get to edit the slides. Okay, so let's look at ammonia. So ammonia is NH3, and this is the Lewis structure for ammonia. Do all of the atoms in this structure have the expected valence, the number of bonds? Yeah, they do. Nitrogen wants to form 3 bonds. It's got 3 bonds. Hydrogen wants to form 1 bond. It has 1 bond. So we're going to expect that these formal charges are 0. But let's look at how we actually determine that. So what we're going to do basically is we remember that each of these bonds is 2 electrons. And this is an artificial idea that humans have come up with. And what we're doing is we're looking at how many of these electrons belong to nitrogen and how many did nitrogen bring in. So when it's talking about half of the bonds, it's saying that for each bond, oops, pointing in the wrong place. For each of these bonds, nitrogen gets to call or to own half of the electrons. So it's kind of like we took this Lewis structure, and the electrons in this bond are being shared. But what if we're going to split everything up? Then we're going to divide the bond electrons equally between the 2 atoms. And so hydrogen's going to get 1 and nitrogen is going to get 1. I think I gave you the example of my husband and I having 6 children, and the shared children we each count as our children, right, in a covalent bond. So this would be like, you know, here's nitrogen and hydrogen have 2 children together, but now they're going to get a divorce and they're going to split everything equally. Okay, it's not actually happening, and my husband and I are fine, don't worry about it. I still like him after all these years. But if we just imagine, if this was split up and we're going to split everything equally, then we would give one of these electrons to the hydrogen and one to the nitrogen. And the nitrogen's going to split up with the other hydrogen and with this hydrogen as well. So that's where the half of the bonds comes from. So what I've circled here are the electrons that nitrogen could take if it split up from all these other atoms.
Wouldn't that be the original amount that it gives, which is 5?
In this case it is, but it is not always that way. So if the formal charge is 0, then nitrogen gets to leave with the same number of electrons that it brought to the compound. But if sometimes there's a formal charge that's non-zero. We'll look at one of those. So here what we're doing is we're comparing the number of electrons that nitrogen owns, which is 5, and the number of valence electrons that nitrogen has. So nitrogen has 5 valence electrons. We subtract the number of electrons that it owns in the structure, and that gives us the number 0. So the formal charge for nitrogen is 0. How many valence electrons does hydrogen have? Just one. It only has one electron. And in this structure, each of these hydrogens has the same situation, doesn't it? If we split those bonds equally, how many electrons does each hydrogen own? 1. So then we're going to have -1 that it owns, and again we're going to end up with a formal charge of 0. So let's do something that's not 0. Let me think of something. Well, let's do hydrogen cyanide. No, not hydrogen cyanide. We need to do cyanide ion. That'll work. Something with a charge. When we have the Lewis structure for an ion, we put brackets around it and we put the charge on the outside. This is the cyanide ion. That's the Lewis structure. And so if we're going to determine formal charge, we're going to look at each of the atoms separately, and we imagine that we're splitting these guys up. So there's an electron for each of them from each of those 3 bonds. So first we ask ourselves, for carbon, how many valence electrons does carbon have? 4. Then we're going to subtract the number of electrons that it owns in this structure. How many does it own in the structure? 5. So 4 minus 5 equals what? -1. So the formal charge on carbon is -1. Let's look at nitrogen. How many valence electrons does nitrogen have? 5. And in this structure, how many does it own? It owns 5. So its formal charge is what? 0. This is an ion. It's got a -1 charge. My pointer's drifting all over the place. If we take the formal charges, there's only 2 atoms in this ion. If we take the 2 formal charges and add them up, they add up to -1, which is equal to the charge. Over here with ammonia, the charge is added up to 0 because it was a neutral molecule. Okay? Any questions? So there will be some practice on the worksheet that I've assigned for today about doing formal charges. So this kind of is out of place. It goes back to the idea of valence. These are what we call normal covalent bonding patterns. So carbon wants to have 4 bonds. It can look like this: 4 singles, 2 singles and a double, 2 doubles, or a single and a triple, any of those combinations. If you see carbon with its 4 bonds, its formal charge is going to be 0 because it's going to get half of each of those bonds and it'll be 0. Formal charge of 0 is more stable than either a plus or a minus formal charge. So nitrogen wants to have 3 bonds. It can do it in these formations. It gets its octet because nitrogen almost always has a lone pair. Oxygen wants 2 bonds. Oxygen's going to end up with 2 lone pairs. It can either have 2 single bonds or a double bond. The halogens are group 7A in the periodic table. That's fluorine, chlorine, bromine, and iodine. They behave a lot alike because they're in the same chemical family. So they're like sisters. They do some things very similar. So we collectively call them the halogens and give them the symbol X. So that could be any of those. They tend to have 1 bond. They have a valence of 1. And then they're going to have 3 lone pairs. So if we look at some different situations, some structures will have formal charges. Now, when you see this line going to nothing, what we're doing is we're focusing on the carbon, and that bond could be to almost any atom. This is just part of this larger structure. And that's a little bit hard to get used to at first. This might be all H's over here. And this would be a radical. Here we've got carbon. How many electrons does it own in the structure? It owns half of those bonds. Oh, that's not the color I wanted. Remember, each of those bonds is 2 electrons, and we're going to cut all the bonds down in half in the middle and share them. So it owns 3, right? But how many valence electrons does carbon have? 4. It has 4 valence electrons minus 3 electrons that it owns in this structure. That gives it a formal charge of +1. I don't know if you noticed in your previous classes, chemists seem to have a thing against the number 1. We don't write the number 1 unless we really have to. And so here, this little plus, that means +1. We'd be like, why bother writing the number 1? It's a plus. And so here is a minus. It's really a -1. Because in this structure, let's make those dots a little smaller. So remember, each of the bonds is like 2 dots connected. So the carbon here owns half of the bonds, and it owns all of its lone pairs. So how many electrons does it own in the structure? 5. And how many did it bring in? How many valence electrons does carbon have? 4. So 4 minus 5 is -1. So this isn't like super hard or anything, it's just a little strange. But we're just kind of counting up electrons to see where did they come from and who has them now. So if you look at all of these different situations, and maybe this is a carbon over here, and then we have another bond. Now this is not the normal valence for oxygen, is it? Here it has 3 bonds. So when you see an atom that has a valence other than what it normally has, a number of bonds other than its usual valence, then you know there's going to be a formal charge involved. And for most organic compounds, when you get formal charges like this that are not 0, then the compound is going to be more reactive because it's going to want to react in a way that's going to give everybody a 0 formal charge. Any questions? Some structures have resonance. So let's, actually I have an example on the next slide that I just made up. My apologies, some of these slides are going to be a little different than what I posted on Blackboard. When we write a resonance structure, these are some rules we have to think about. You can't change the relative positions of the nuclei, of the atoms. You can't rearrange the atoms and call it a resonance structure. The differences between resonance structures are just in the positions of either multiple bonds or lone pairs. The atoms don't move, it's just the electrons moving around. Whenever possible, we want to adhere to the octet rule. The octet rule says everybody gets 8 except hydrogen, he gets 2. And we're going to prefer formal charges of 0. So let's look at an example of something that has resonance. So carbonate ion. In case you have forgotten, carbonate ion is CO3 with a 2- charge. So when we draw the Lewis structure for carbon, we're going to put carbon in the middle. Generally, molecules are going to have a symmetrical arrangement. So if you have one odd one, like the carbon is odd, and there's only one of it, and then there's multiple oxygens, we'll put the carbon in the middle and put the oxygens around it instead of making a long chain or doing something funny. So we'll put the oxygens around the carbon like that. And then drawing a Lewis structure, we need to think about the total number of valence electrons that we have available. We have one carbon atom, and carbon has 4 valence electrons. We have 3 oxygen atoms, and how many valence electrons does oxygen have?
5.
Close, 6. And then this charge, a 2- charge, does that mean we have 2 extra electrons or that we're missing 2 electrons?
2 extra.
2 extra. So we have to add 2. Negatives can be very confusing. So this is 4 and 2 is 6, so that's 24, right? So we have 24 electrons to show in this structure. So we've already got 2, 4, 6. Now, carbon wants to form how many bonds?
8.
Well, it wants 8 electrons, but how many bonds? 4. That's what we called the valence. So let's give carbon 4 bonds by doing a double bond with the oxygen. Is this oxygen going to like the 2 bonds there? Yeah, it is. Because oxygen has a valence of 2. Can we make these other oxygens happy by doing double bonds with the carbon? No, because then carbon would violate the octet rule. It would have too many electrons, so we can't do that. So this is kind of like life. You know, you can't make all the children happy at the same time. So you just have to choose one and make them happy. So this is the lucky oxygen today. So the carbon's happy and the oxygen's happy, and these 2 oxygens, they're just out of luck. So we've got 2, 4, 6, 8 electrons, and now we're going to distribute the remainder around and see if we can at least get octets for all of these guys. Carbon doesn't need any lone pairs. I said 2, 4, 6, 8. Here's 10, 12, 14, 16, 18, 20, 22, 24. So we didn't satisfy the valence for all of the atoms, but at least we got everybody to have an octet. And then because this is an ion, we want to put brackets around it and put the charge on the outside of the brackets. I think one of the reasons that we do that is so that the 2- doesn't get lost in all the dots. Just kind of calls attention to it. So any questions about how I drew that one? Yes?
If oxygen only has 6 valence electrons,
Mhm.
how do they get the full 8?
Like this one or like this one?
Well, the
Both of
2
them.
other ones.
These
Both-
2?
Yeah.
Okay, how do they get 8 valence? How do they get 8 electrons in here if they've only brought in 6? That's where the formal charge idea is helpful. Because yes, oxygen only had 6 valence electrons. What's happening here is that we're having some sharing. We have these 2 extra electrons, and so one of those extra electrons goes in here to make this bond with carbon. The other one's going in here. So let's look at the formal charges of these different atoms. So for the carbon, does it have the same number of bonds as its expected valence? It does. So we could go ahead and calculate it out, but it's going to be the same. Usually if the valence is 0, we don't write it on the structure. We only write the ones that are not 0. What about this oxygen? What do we expect the formal charge to be? Well, it's got 2 bonds. Is that what oxygen likes? Yeah. So we expect this to be 0. Let's check. Oxygen has 6 valence electrons. How many does it own in the structure? 6. It's got these 2 lone pairs, that's 4 electrons, and then it gets half of each bond. So 2 more, so it's 6. So it's got a formal charge of 0. Let's look at this guy. So 6 valence electrons for oxygen. How many does it own in the structure?
7.
It owns 7, doesn't it? Because it gets this guy. So 6 minus 7 equals minus 1. Is this one going to be the same or different? The same. So what we would do is next to this O somewhere, we'd put a minus. That didn't work out very well. We put a minus and circle it. And this is going to have a minus that's circled. And that indicates the formal charge. Yes?
So the fact that it's 2 negative has nothing to do with the fact that the valence, or the dots on the left-hand side oxygen are missing, or it does.
It's related. Because when we look at these formal charges, this one is 0, that one's 0, this one's minus 1, this one's minus 1. The formal charges have to add up to the charge on the molecule or the ion. Okay? Because this is an ion with a -2 charge, then we're okay having these 2 -1 formal charges. So this is going to be the same for both of those oxygens. And that's going to add up to a total formal charge of -2, which corresponds to the charge on the ion. And so really we could think about that red one and this red one. We could say, well, those are the extra electrons. But really how it works is the electrons just, it's like going to a potluck or something, and you just pool, you put all the cookies together. And it's not, oh, these are my cookies, and those are your cookies. It's just a big pool of cookies, a big plate, a big table full of cookies. Sorry if you guys missed lunch. I talk about food sometimes. I like cookies. So the electrons are like that. You know, so-and-so brought this many electrons, and no, it's not always exactly fair. Formal charges is where we actually do figure out, oh, are you getting more than you brought? And sometimes that happens. So here oxygen is getting 7 electrons even though it only brought 6. And so the formal charge measures that. Does that help? Any other questions? Because this is a new idea, this whole formal charge business. Okay, so going on to the rest of this idea about the resonance structures. Well, why does this oxygen get the double bond? Why doesn't this oxygen get the double bond? Is there any difference between those oxygen atoms? No. We just had to pick one, right? Well, let's do it again and pick somebody else. So here's carbon, and this time we'll do the double bond with the oxygen on the right. And then we end up with the same number of lone pairs all over the place. And I'm kind of squishing these together. Is this structure any better than this one? No, it isn't. These are actually resonance structures. The arrangement of the atoms has not changed. The only thing that's changed is the location of the double bond and the location of a lone pair of electrons. And so what we do is we say those are resonance structures, and we indicate that by drawing a double-headed arrow between the structures. So basically, we're looking at this central atom, and there's a double bond here, and there's 2 other identical atoms without double bonds. And so we need to try all the different options. There's one more option, isn't there? Give the double bond to the guy on the bottom. Let's see if I can squeeze all this in here. And that is a third resonance structure. It's supposed to be an O. I don't know what happened to it. Now, let's look at the formal charges on the atoms in this middle structure. What's the formal charge on the carbon? 0. The fast way to do formal charges is to remember the valence for carbon. The valence is the number of bonds that carbon would like to make. Carbon wants to make 4 bonds. Here it has 4 bonds. He's good. He's got a 0 formal charge. And this oxygen wants to form 2 bonds. Here he's got 2 bonds, and so the oxygen here has a formal charge of 0. What about this oxygen? It's going to be 1 minus. It's the same calculation as for this one. It has 3 lone pairs and half of the bond. So this one has a -1 formal charge, and this guy down here has a -1 formal charge. And in this other structure, that one and this one have the -1 formal charges. So could we have a molecule where the bonds are shifting around all the time? Like, I don't know, you tell us all kinds of things that we don't think are possible. What actually happens is that it's like a hybrid of these 3 different things. So if you have a dog that comes from the father being a Labrador Retriever and the mother being a poodle, does that dog like shape shift between being a retriever and a poodle? No. You call it a Labradoodle, and it looks kind of like the mother and kind of like the father. That's kind of like actually what our children are. My husband's Japanese and I'm of Swedish descent, and so the kids are all like cookie cutters, but they don't really look like either of us, but they all look alike. It's kind of funny, actually. But what happens is the actual molecule here is a hybrid. It's intermediate between all 3 of these. But Lewis theory, this method of indicating structures and where the electrons are, is limited and has no good way for showing that. And so this is the best we can do. What actually happens is that this second bond here is actually shared by all 3 positions. And so there's actually, this is 1 1/3 bond, and 1 1/3, and 1 1/3, and the extra charge is distributed all over. And that's an important concept for organic chemistry. They don't teach you that in 3A because you don't need it for general chemistry that much. They talk about it a little bit, but we do need to understand this idea of resonance for organic chemistry. So what we do is we're basically showing, well, this is like one of the parents and one of the parents and one of the parents, but the actual molecule would be like if you mix them all together. Any questions? Sometimes when you can move electrons around and do different resonance structures, you end up with structures where the formal charges are not all the same. Here we have a -1 formal charge on oxygens, on 2 of the oxygens, and it's just a difference of where the formal charge ends up. Sometimes you can end up with a molecule where one of them will have a formal charge of all 0, and another one you might have a +1 and a -1. The one with the lower formal charges is going to have more influence. If you look at my kids, you'll tell that my husband has more influence on their appearance than I do. They all have dark brown hair. I have blonde hair. There's no blondies. Nobody has green eyes. So he has more influence on them. We'll probably come to stuff like that later. Here's another, I don't know why, another slide with common bonding patterns. I'm just going to skip over that because we have a lot of other things to talk about. This is another kind of duplicate. This goes back to the idea of valence. Hydrogen has a valence of 1, carbon's 4, nitrogen 3, oxygen 2, and the halogens are 1 bond. So we use arrows in organic chemistry in a slightly different way. Straight arrows in a chemical equation. Let's just make something up here. Nah, that's not what I want to make up. Oh, let's use purple. I don't know why. If we have something like A goes to B, that's what you kind of think of as a regular chemical reaction. And this implies that most of the A gets converted into B, or maybe even all of it. But sometimes we have half-headed arrows, like this, pointing in both directions. Oh, I need something over here. And that indicates that the reaction is in equilibrium. A is going to B and B is going to A, both at the same time. It's a little bit like traffic on the freeway. There are people going south on 99, and at the same time there are people going north on 99. And it's a back and forth thing. And it's called a dynamic equilibrium because the cars at the north end and the south end are always changing, even though there may be the same number of them. So that's what the half arrows indicate. If we have the double-headed straight arrows between two structures, that indicates that those are resonance structures. So that would be something like this. I don't feel like making up an example, but we just saw that when we talked about resonance structures. So double-headed arrow. Then we have curved arrows. So those were the straight arrows. Then we have curved arrows. I need an example of this. I'm going to look in here real quick because it'd be great if... So I didn't leave enough room. So I'm going to give the example of the full head arrows right here. So if we had something like this, a curved arrow with a full head, meaning the arrow has both of its arrowhead pieces. I don't know what you call those. That means that a pair of electrons, there's two little angles, right? There's this guy and there's that guy. One for each electron. Two electrons are moving. And so that would indicate that those electrons are going over here. So this arrow is showing that these electrons, well, let's make those a different color, that might help. That the electrons from the double bond are now becoming a lone pair on the oxygen. Would these two things be resonance structures? Do they differ only in the position of multiple bonds and or lone pairs? Yes. They both have carbon and oxygen, and whatever these things are didn't change. All that's changed is this double bond became a lone pair over here. And so we would put a straight arrow with a double head in between, indicating those are resonance structures. Oh, just for grins, let's look at the formal charge. On this guy over here, what's the formal charge on the carbon? How many electrons does carbon have as an atom, valence electrons? 4. How many does it own in this structure? Half of each bond. There's 3 bonds. 1, 2, 3. So 4 minus 3 is plus 1. So it has a plus formal charge, and this oxygen has what formal charge? Has a minus 1. Because oxygen has 6 valence electrons, but in here it's got 2, 4, 6, and half the bond is 7. 6 electrons minus 7 is negative 1. These formal charges add up to 0, which is the charge on the molecule. Okay? So in these resonance structures, this one has 0 formal charge, this one has non-zero formal charges. This would be the more stable structure. When we have a half-headed arrow, we have 1 electron moving. Let's see what their example for that one is. So if we took something like this, I'm going to make these arrows a little different colors. So if I go a half, ooh, that's not right. I'll go with green, I don't know. A half-headed arrow, that means that one electron is going in that direction. The other half-headed arrow is the other electron. So there's 2 electrons in here. So what we end up with is the carbon is still bonded to its hydrogens, and this carbon is still bonded to its hydrogens. But now there's 1 lone electron on each of those guys. And these are radicals because they have an odd number of electrons.
Does that mean that electrons are not coming back and forth?
Right.
It's not a resonance structure?
This is not a resonance structure because there's a bond that's broken. This wasn't a double bond. This was the single bond. In this structure up here, it's the second bond, the multiple bond that's moving around, and lone pairs. Here, it's the original bond. So if you have a double bond or a triple bond, and the second or third of those bonds moves around, it can be a resonance structure. But here, that bond actually got broken, and so now these are 2 fragments that can actually go away from each other. They're not connected anymore.
What was that called again?
These are called radicals. And I think I mentioned those on Tuesday. These are radicals. Sometimes, people who are into health and nutrition talk about, oh, we need to take more antioxidants to protect ourselves from free radicals. There are free radicals that are generated in your body, in the environment, and antioxidants like vitamin C do help to take care of those free radicals. Radicals are very reactive, and sometimes they react in ways that are not beneficial to your health and well-being. So I guess we would put an arrow here because this went from this to that. Any questions? We'll be using these arrows as we go along. I think I'll stop the recording here.